you can make your risk of H sharp to go to 0 is if somehow your class H is large enough that it actually includes your unknown function f that you're after. So you'd like to take M to go to infinity. You'd like to say, I'm going to use an infinite class. And unfortunately, if you do that, your bound is terrible because it tells you that for the bound to be meaningful and to say that you're going to generalize with high probability, you need a number of samples that explodes. And what this result is highlighting is it's highlighting a fundamental trade-off of learning, which I'm showing here pictorially in that slide. It's telling you the following. It's telling you that if you plot a risk as a function of the richness of the hypothesis class, and for us right now, richness means the size of the class, and we'll spend a lot of time in a few weeks refining that, coming up with a different measure of richness. But for now, it's the number of hypotheses in the class. What we're saying is we're saying that as the size of the class increases, we should expect the following. The true risk of the best hypothesis H sharp is going to go to 0, just because you have more models to choose from. They are more likely to better fit your unknown function. The empirical risk of H star is going to go to 0. Why? Because eventually, remember, your data set is of a fixed size n. So if you increase the complexity of the class, you will have eventually a function that is almost able to memorize what you're trying to do. And therefore, the empirical risk is going to be, if not 0, then close to 0. But unfortunately, what we are saying here is that there is a regime where the bound is useful. Because there is a trade-off between the size of the class H and the number of samples that you have in your data set. And the number of samples in the data set has to be large enough compared to the log of H if you want to generalize well. If it's not the case anymore, then you will lose all the guarantees. And if you make an experiment, we'll do that during the next lecture, you will see that actually, even though your empirical risk of H star goes to 0, your true risk of H star actually goes up. If you look at that curve, there is a very sweet spot where your true risk of H star is minimum. If you are above that sweet spot, you are in a situation that's called overfitting. This is the situation where compared to the size of your data set, the richness of your hypothesis class is too high, and therefore you're memorizing. Memorizing is not generalizing, and that's why you have a bad performance where your empirical risk is not at all close to your true risk for H star. If you are below that sweet spot, you are underfitting. What's happening in that regime is that you can generalize very well, but your baseline performance for H star is pretty bad. And finding that sweet spot is very tricky, and that's what a lot of people in machine learning try to identify carefully. So we'll talk about what it means from a more practical perspective, but you see that that first analysis already gives us a lot of insight as to the problems we will face when we talk about machine learning in terms of the trade-off between the size of the model, here measured by H, and the number of samples that you have access to. So one thing I have to admit to you is that this is a traditional view of machine learning. And most of the class is going to be about that view. But if you think about deep neural networks, they don't fit that picture. Because deep neural networks operate in a regime where the number of parameters that you have in your model is insane. You potentially have an infinite number of models, but even just the sheer number of parameters, the weights in your neural net that you can tweak compared to your data are insanely large. And so they operate way to the right. So how does that fit? So I'll try to give you a glimpse as to what's happening in these modern machine learning techniques. So let me extrapolate just a little bit here. So that's just going to be an illustration. If you were to actually continue that plot, you would see the following. If you were to look at the true risk, you would see something like this. It would peak, and then you would observe a decrease. And the decrease actually meets the empirical risk here. And that weird threshold here, that threshold that I'm plotting here in blue has a name. It's called the interpolation threshold. And this is a threshold beyond which your model is even beyond memorizing. The size of your model class is so large that weirdly enough, you start not just memorizing, but you're able to interpolate between points that you have memorized. And if you're interpolating, you're actually learning pretty well, because if you get an unseen sample, it will be between points that you have memorized, and you can interpolate what is the label of that point that you have not seen yet. And deep nets operate in that weird regime. There's a lot of super cool, exciting work going on in machine learning right now to formalize that. That brings us to the last topic I wanted to address today, which is probably approximately correct learnability. So let me start with a definition. Probably approximately correct is often abbreviated at PAC. And it says the following. You say that the hypothesis H, so that's a set of models, is PAC learnable, and sometimes it's called agnostic PAC learnable. But PAC learnable, if you can find a function that gives you the number of samples and a learning algorithm such that the following is true. For every epsilon delta, which are small parameters that compute, that tell us the epsilon, how well you generalize, and delta is, what probability you will not generalize. For every px, py given x used to generate your data, then if you run the algorithm on at least nh as a function of epsilon delta samples, id, then the algorithm will return an hypothesis h such that the probability that R of h differs from the risk of h sharp being the minimizer of the true risk, by more than epsilon is going to be less than delta. Or equivalently, the probability that it's less than epsilon is at least 1 minus delta. Okay? So the reason it's called probability, the probably approximately correct learnability, is because this less than epsilon here, this is the part that says approximately correct. You're not guaranteeing that your risk R of h returned by your algorithm is exactly the best one, but it's close, it's epsilon close. The second part here, 1 minus delta, that's the probability. If you remember, one of the very early points we made in the last lecture is that you have to forget about being possible or impossible. You have to talk about probable versus improbable. And here we're saying that it's very probable, delta being small, 1 minus delta is close to 1, that we actually generalize well. And I have a question from 01. What is the meaning of 01? I do apologize for that. It's one of my quirks as a former French student in France. 01 means here, when I write 01, it means that this is the set of x's such that x is strictly greater than 0, strictly less than 1. So it's the interval, but I remove the boundaries. And I know that in the US, people write 01 like that, but I think that's a source of confusion because your parenthesis becomes bar very quickly and you don't know. So it's just my notation to exclude the boundaries of the interval. So it's the interval 0, 1 open on both sides. So that's the PAC bound. That's the definition of PAC learnability. A couple of comments are in order. There are a lot of subtle points about that definition. If you look at epsilon and delta here, this bound has to hold independently of what px and py given x are. And that's super important. Remember, we had to introduce px and py given x in our learning model to even talk about learning. But these are quantities we don't know. And so PAC learnability requires you to have a bound of that form that holds independently of the true nature of the distribution that was used to generate your data. And that's a very fundamental result, therefore, because it's telling you that even though you don't know how your data is generated, the existence of a probability is all you need to actually obtain that bound. And the challenge in PAC learnability is to figure out a very good value for that number of samples that you need as a function of epsilon and delta. Now, the good news is that through the discussion that we've had today, I eased you into this analysis. And I will have you make sure that you understand how by having you formalize that into a homework. But if you piece together everything that we've done today, you will find that we have effectively proved that a hypothesis set H, which is finite, is PAC learnable with an algorithm called the empirical risk minimization H divided by delta over epsilon squared. So this is effectively what we proved in the previous slides. This NH is called the sample complexity. It's the number of samples that you need to be epsilon delta pack learnable. So that takes us to the end of the lecture. What we have proved is we have proved that under some conditions that kind of strike a good trade-off between the number of samples that you have in your data set and the size of the hypothesis class, you can generalize. There's a hope that you can actually learn something useful. And we demonstrated that by developing a pack bound for an algorithm that's called the empirical risk minimization. There are other ways to do that. Don't think that the only way to come up with a good model is to do empirical risk minimization. We will come up with new techniques, especially when we talk about support vector machines that don't minimize the empirical risk and yet generalize pretty well. So it's one way to do it, but at least it was a good segue into showing that learning is possible, but there are constraints. And the main result that we obtain is that there is that trade-off that is sort of unavoidable. We're doing a lot of work to show that the true risk of the minimizer of the empirical risk is not too far away from the true risk of the best minimizer of the true risk. But that in itself doesn't mean that the best minimizer, our H chart, has a small risk itself. What we would like is we would like to not only generalize, but also be lucky and guarantee that R of H chart is close to 0. And in general, as I said, that's not possible because you have that trade-off between the richness of the hypothesis class and the number of samples. There are many problems where there's no hope anyway to have a small risk. When it comes to classifying cats and dogs, there are certainly somewhere in the world cats that look like dogs and dogs that look like cats. And these will never be able to classify perfectly. So you have to forego this idea that you can achieve a 0 risk. What you hope for is to get a small risk. But there are a couple of lingering questions. If we accept the fact that the risk cannot be 0, then what is the best value of the risk that we can achieve? And how small can we make the risk of that minimizer H star of the empirical risk that we have found? And we will start addressing this question when we'll talk about the Bayes classifier.